Okay, we've got an integration worked example here, which is not completely straightforward. This is area under a curve, but it's a little bit more complicated now because we've got not only the area under the curve, but we've got a straight line to worry about here. So there's a bit more to it. The diagram shows the curve y equals 4 cos 2x divided by 3 minus sine 2x for x greater than 0, and the normal to the curve at the point pi by 4, 0. Show that the exact area of the straight shaded region is this expression here, natural log of 9/4 plus 128th pi squared. So, all right, we know we're in for a bit of a challenge here. And when we see 10 in brackets there, it looks like it's going to be a bit of a beast, doesn't it? But actually, it's not too bad, and there are some good learning points in here, so that's why we're having a go at this one. Right, so we can do this integral here of this the shady bit that's above the x-axis. That's just the integral of the curve, not totally straightforward, but we can do that. But we need this the area of this triangle as well here. Now we can find that if we know what this intercept value is, because then we'll have half base times height, and we'll know this intercept if we can find the equation of the line. We can find the equation of the line because we've got a point here. So as long as we know the gradient of it, then we can do that. And we can find the gradient of it if we can find the gradient of the curve at this point, because then we've got perpendicular lines, and the product of the gradients of perpendicular lines is equal to -1. So that gives us a fighting chance. So let's find the gradient of the curve at this point. So here's our function, and what we're going to do here is we're going to use the quotient rule for differentiation, which just a reminder then, the derivative of f divided by g, f of x divided by g of x, this is your f, this is your g, is equal to f prime, which is the derivative of f, times g minus f times the derivative of g, all divided by the g squared. Okay, so so let's go through that. Dy dx is, well, this is your f prime, this is your derivative of the numerator, times the denominator minus the minus the numerator times the derivative of the denominator, all divided by the denominator squared. Right, we want to evaluate that at x equals pi by 4. Now, that's not too bad because these are all 2x's. So when we actually work out 2x, it's pi by 2, and sine of pi by 2 is 1, and cosine of pi by 2 is 0. So basically, we just have to plug the appropriate values into here. This whole term, in fact, drops out. And we're left with this calculation, which is going to give us -4. So that's the gradient at that point, which is about right. It's going to be negative and steep. So yeah, that's fine. And therefore, the gradient of the normal is going to be the negative of the reciprocal, which is going to be 1/4. So that's sort of shallow and positive. Now, skip a step or two here, really. I mean, this is kind of GCSE stuff. Basically, given the point and the gradient, we can work out the equation of that normal, therefore, is this. And because it's explicit in y, this bit obviously is there for the y-intercept. So that's that value there. So we've got no problem now with the triangle bit below the x-axis. So let's go back now and let's kind of look at the integral. What we're going to do is do it in 2 parts. We don't have to do that, incidentally, in general, and I'll come to that in a few minutes. But first of all, let's do this. Do the integral of or the area under the curve. So the area between the curve and the x-axis is given by this integral as we integrate the function between 0 and pi by 4. There we go. dx, we're basically summing all the infinitesimally small strips between the x-axis and the curve. Right, okay. Now, the thing with this one is spot the dog, if that means anything to you. If you imagine that we started with this function here and we differentiated this, and this is a composite function. The outer function is the natural log. The inner function is 3 minus sine 2x. So what we would get as a result of this is the derivative of the outer function with respect to the inner function times the derivative of the inner function. And the derivative of the inner function is going to involve cos 2x. So this looks like it could be the reverse chain rule. All right, so in order to do this, we're going to let u equals what we think is the inner function here on the denominator. We need an expression for du because we're going to have to integrate with respect to u. So if we differentiate both those sides, then what we're going to get is minus 2 cos 2x dx. All right, looks like we're in with a chance. So just doing that substitution there, we're going to keep our 4 cos 2x in there, but our 3 sine 2x becomes u. And then just rearranging this lot here, our dx becomes du divided by minus 2 cos 2x. And now you can see we've got this cancellation going on there. So it is indeed reverse chain rule. So so those cancel. We've got 4 over the minus 2 there, which is going to take outside the brackets. And so what we've got is the integral of 1 over u du between these two x limits. Now they are x limits. We can't apply these without converting back. We're going to do that in a minute. But before we do that, what we can do is we can actually get rid of this minus sign by swapping the limits over. Okay. So that's what we've done there, which is just one way of doing it. It's a little bit simpler, I think. So so that's what we've got, is having integrated 1 over u du. That is one of our standard logs that we should be able to remember. So that's going to be 2 natural log of u between these two x limits. And then we can convert back by substituting back our u, we've got 2 natural log of 3 minus sine 2x between pi by 4 and 0. Now, if we just work that through, again, we've got pi by 4, so 2x is going to be pi by 2. So it's going to give us this expression here, 2 into natural log of 3 minus the natural log of it, which is going to be 2. So we've got the difference of 2 logs, which is therefore the quotient of the log of the quotient. And this 2 here, of course, and using our log rules, is going to be the square of it. So it's actually going to give us the natural log of 3 divided by 2 squared, which is the natural log of 9 over 4. Right. Now, so we've done the area under the curve down to the x-axis. Now, the area of the triangle, well, basically it's just half base times height. One of these is the base, the other is a height, whichever way we look at the triangle, and that's going to give us pi squared divided by 128. So here we go. We've got this and this. Total area equals that, which incidentally comes out to this sort of figure here. So that is it. There's your 10 marks. I think just a little footnote to this actually is when we've done these two separately. We could actually do them in one integral. In this case, it doesn't really help us very much, but in the general case, then what we're actually doing is we're actually summing all these lengths here, these infinitesimally narrow lengths between 0 and pi by 4. So this that's what this expression is here. Okay, so we can integrate that between 0 and pi by 4. We will actually come up with the same thing. One thing we have to be a little bit careful with our integrals below the line is that unless we apply you know, sort of the correct sign, then we're going to end up with a negative area here, and that's going to give us a kind of a potentially the wrong answer. But here, you know, all these distances are this expression here, obviously a function of x. So we could do this. Say it doesn't help on this particular one, but it might do in other circumstances, particularly where you've got the area between, say, two curves. So it would be rather more complicated. Right. Okay. So that is it. As I've said, a little bit of a beast, but we have kind of gone through, you know, finding the equation of the normal. In this case, we're using the quotient rule and evaluating that at the point where we need to. And we've looked at the reverse chain rule, or spot the dog, if you like, for something which is not completely obvious that's going to be possible. But we spotted that was the derivative of the inner function. And we've worked that through, and lo and behold, we've got the answer. So hopefully that's been useful and interesting. And thanks for listening.